Good evening. I'm Jim Robertson, and this is Ideas. Tonight, Beyond Clockwork, consideration of the limits of man's universe. La Reine Verte, the Green Queen, Earth. The full extent, the final limit man's mind encountered for several thousand years.
Cosmology and cosmogony. Cosmology is the study of the content and form of the universe. Cosmogony, the theoretical study of the universe's inception, its very coming into being. Man, as the philosopher, then the astrologer, finally the astronomer-physicist. Man has passed through these approaches to the universe and come, in the 20th century, to two ultimate sciences, studies which encompass everything under and even beyond the sun.
Even the philosophers of pre-Hellenic Greece were concerned with the meaning and order and creation of everything. It is simply that man has extended his theoretical studies of the universe as he has developed new positions or vantage points, as well as new tools of exploration. Until he possessed the trigonometry to measure the distance from the Earth to the stars, he could not deal with them as other than the pinpricks of light stuck onto a fixed firmament. Early notions of the universe amounted to rational myths. As late as 55 BC, their rationality remained severely qualified by rather fanciful hypotheses. In his historical library, Diodorus approvingly sets out the views of the Ionian Greeks.
When in the beginning the universe was being formed, both heaven and earth were indistinguishable in appearance, since their elements were intermingled. And then, when their bodies separated from one another, the universe took on in all its parts the ordered form in which it is now seen. The air set up a continual motion, and the fiery element in it gathered in the highest regions, since anything of such a nature moves upward by reason of its lightness. And it is for this reason that the sun and the multitude of other stars became involved in the universal whirl.
If we go still further back, to the year 600 BC, we find man confronting a universe amounting to little more than a patch of flat ground, a universe even Diodorus would have found laughable. The universe of the Babylonians and the Persians was a flat earth enclosed by a box.
We know that we can look out across the plain and see very far. Only the mountains in the distance prevent us from seeing to the edge of the earth, where all is water and nothing more. This we can see. As to why the water does not simply roll off the edge and away from the land, we answer that the sky is a firmament to which the stars adhere, and that it is like the lid of a box, nested firmly upon the sheet of earth, with its edges damming back the waters of the sea. This we cannot see, but how can it be otherwise?
The early Greeks could see no other explanation either. But their love of symmetry led them to an admiration of the circle, and this led them to see the earth as a circular slab, overfitted with a dome of the heavens. The earth consisted of an island of land, round which flowed the ocean river. The Mediterranean Sea led from this river into the heart of the land. Unlike their fellow Mediterranean peoples, the Greeks went so far as to measure the dimensions of the universe. Around 500 BC, Hecataeus of Miletus set the diameter of the slab at 5,000 miles, giving the earth a surface of some 20,000 square miles, an enormous range for the Greeks to consider. But the Greeks were also philosophers, were logicians, and this flat earth led to enormous difficulties for them.
What keeps the universe in its proper place? And is there a where to this place? In our world, down is a direction, and only one. Things heavy fall there. Shouldn't the earth as well be falling? If so, then would it not fall forever? Would it not plunge into infinity? Well, that is too much to accept. We've heard of the foolish people of the East, who place the earth at rest on 4 pillars, and the pillars on elephants, and the elephants on an enormous turtle, and the turtle in an ocean, and the ocean... But you see our problem. This universe is very much what we see, but for what we cannot see of that we have no suitable answer. Who can believe in infinity?
It was Anaximander of Miletus, a contemporary of Hecataeus, who suggested man lived not on a flat surface, but rather upon a cylinder. He reasoned so because travelers going north see new stars appearing before them, while old stars fade behind. If the earth curved in a north-south direction, then all stars would not be constantly visible.
But what do we make of the mysterious disappearance of ships? If I am in a boat in the middle of the Mediterranean, and another boat sails away to the east from me, I first see the hull of the ship disappear, later the masts, and finally the topsail. And this is true of a ship departing to the north, to the south, to the west as well.
Philolaus of Tarentum proved the earth was a sphere in 450 BC, 1900 years before Magellan clinched the matter by circumnavigating the globe. Infinity was set aside again. A spherical earth would fall towards its own center, and if the earth were the base of the universe, then it naturally followed that the universe too would be a contained sphere with the earth at its center. And man could now move from the earth to solar system, a great step in his development of cosmology.
The Pythagoreans of Athens constructed a model of the universe in which a central fire lay at its heart, circled first by the earth, balanced by a counter-earth, then following in greater circles by the moon, the sun, and planets. Roundness and symmetry, they searched their own culture for a notion of perfection and transferred it to the design of the universe. Plato supported them in their elevation of roundness as the universal ideal. The sphere was the figure most like to itself, and since the like was more beautiful than the unlike, the universe would naturally have the sphere as its fundamental pattern.
The Platonists put aside the notion of a central fire and ensconced the earth at the center. But men were beginning to make more meticulous observations of the heavens. What they found there was disturbing. They had thought of the outer sphere as fixed points of light upon a fixed firmament, with only the sun and moon in motion. Now they found movements in the sky tent, in particular Mars, the red planet, which seemed to describe lazy but irregular motions in the night sky.
This motion in which the planet seems to loop back upon its path is called retrograde. It could not be accounted for in the Platonic system. What was needed was a new model of the universe, one which would take into account such motions.
Eudoxus of Cnidus, one of Plato's pupils, made such a model in 380 BC.
The Earth is at the center of a series of concentric, transparent spheres. Each sphere rotates on a different axis at a different but constant velocity. Upon each sphere is affixed one of the wanderers, Moon, Sun, and the 5 planets, Mercury, Venus, Mars, Jupiter, and Saturn. These 5 have 4 spheres of motion, the Sun and Moon, 3 each. The whole of the universe is enclosed by an outer sphere, which contains the fixed and unmoving stars.
Aristotle assumed the system of Eudoxus with its 27 spheres. But Aristotle gave it life, gave it reality. Eudoxus had conceived of his model of the universe as a mathematical calculator, a device to help one predict future positions of the 7 moving celestial bodies. As such, the model worked perfectly well. But Aristotle took the model for the plan of reality and improved it by adding 21 insulating spheres between the planetary ones, so as to give his universe a solidity and connect all the parts into a whole, into a perfect organic universe.
Aristotle is in error. He was no observer of the heavens. One looks at the heavens long enough, one sees that the fixed stars constantly change their position from day to day, season to season. There can be only one thing to account for this. The Earth is not fixed, not permanent. It is not at the center of the universe. Rather, the Earth too rotates on an axis, together with all the other planets, round the sun.
Aristarchus of Samos, around 250 years before Christ.
Aristarchus hit upon the most accurate conception of the solar system possible. He still thought of the solar system as the totality of the universe, but he accurately described planetary motions and invented the heliocentric model to no avail. Aristotle made it very clear he regarded the Earth-centered universe as the most perfect and therefore the only possible design. The philosopher also regarded the universe as eternal, believed that it would last forever, had lasted forever. For him, all created things must decay. Therefore, the universe cannot have been created. Its perfection and beauty was proof of its eternal life.
Aristarchus fell into oblivion. Aristotle became the philosopher. Claudius Ptolemy enshrined his earth-centered system with his own work, the Almagest, or greatest of books, as the Arabs were to call it.
Ptolemy fleshed out the Aristotelian model through mathematics. He corrected errors of motion through an ingenious system known as epicycles. As a mathematical model, it served the astronomer well in predicting the courses of the planets. But it left the universe limited to the solar system, and it left a singular misconception which would reign through the Middle Ages. Christianity, the new Western religion, was perfectly happy to accept Aristotle and Ptolemy and believe man's home, Earth, to be the center of the universe, though church fathers would insist on creation by God from nothing. All that had been won now seemed to be lost. The Roman Empire broke up. The Muslims swept even into Europe, carrying Ptolemy with them. As the Catholic Church consolidated its position and its power, it naturally acquired a vested interest in preserving the shaky status quo in all things. Grudgingly, it admitted Aristotle for its intellectuals, but permitted all manner of absurdity and literal superstition to develop among the people. Cosmas, an Egyptian monk, gave this picture of the universe in 540 A.D.
In accordance with Holy Scripture, we may easily read the shape of the universe, which is that of the Jewish tabernacle. Now, that is to say, it is as an oblong box containing 2 layers, one above the other. Lower is the visible world, including man, earth, and stars. The earth is flat, twice as long as it is wide. Firmament, a word which scholars tell us means impermeable wall, separates our lower level from the upper, where live the angels. They move the sun and planets and moon about to light the earth and are also responsible for opening the windows of heaven, permitting the waters above the firmament to wash over the earth.
What did it matter that the intellectuals knew better? Be it with Aristotle or Cosmas, the church was secure, with a world of infinite perfection, of clockwork precision, ordered by Almighty God, set in motion by him at the instant or 7 days of creation.
Those men who could truly be called scientists, who observed, gathered data, made calculations, and drew conclusions, those men were still limited to drawing hypotheses. No concrete alternative to Aristotle and Ptolemy was raised for 600 years, and then by a man who published only on his deathbed the salutary dedication of his work to the reigning pope.
Nicholas Copernicus was born in Poland in 1473. He studied at several universities and entered the service of Holy Mother Church as a canon. He first issued his theory of a sun-centered universe in a brief outline form, circulated among friends who urged him to publish, including all his proofs and details. He finally gave in to them, and a copy of his book, On the Revolutions of the Heavenly Spheres, reached him on the day he died, in 1543. Unbeknownst to him, his clergyman publisher had added an additional introduction to the book, asserting the author offered it only as a hypothesis and giving the impression Copernicus himself didn't believe the theory.
Copernicus replaced the Earth with the Sun as center of the universe and had the planets describe perfect circles round our star. In addition, he placed the Moon in orbit round the Earth, something his critics would use against him. Why didn't the Moon, too, orbit round the Sun? There were no other cases of such fracture in the visible clockwork.
Fortunately for Copernicus, he died before he could become embroiled in the kind of vicious academic argument endemic of his age. Unfortunately for us, no one paid much attention to the book, and 50 years' good work was lost. If any question was reopened, it was the philosophical one of the finity or infinity of the universe.
In my system, I have encircled the sun system with a sphere of fixed stars. I have not done so because I truly believe this, nor do I disbelieve. It is hardly significant to the working out of the universal system I offer, and I leave this question to the philosophers.
Copernicus left his infinite possibility and his system of spherical orbits to be further unriddled by others, like Johannes Kepler.
Kepler succeeded the Danish astronomer Tycho Brahe as imperial mathematicus to the Austrian emperor at Prague. Brahe left him a wealth of observed material concerning planetary motions, and Kepler took these, along with the Copernican system, and perfected his 3 laws of planetary motion. The first 2 were published in his New Astronomy in 1609.
My first law is a simple correction of Copernicus' design of perfectly circular orbits for the planets. It is that the orbits of the planets about the sun are ellipses with the sun, located at one focus of the ellipse. The second, and concomitant law, is that while a planet is circumscribing its orbit, the line joining the planet to the sun will sweep out equal areas in equal intervals of time.
His third law was set out in 1618 in a volume entitled Harmonice Mundi, or the Harmony of the Worlds.
The square of the period of any planet about the sun is proportional to the cube of its mean distance from the sun.
Well, that seems enormously complex, but what it simply does is establish a mathematical formula, a direct relationship between a planet's distance from the sun and the length of time it takes to circle the sun. It became a useful tool in measuring the sizes of planetary orbits and dictated the end of any scientific acceptance of spheres.
The 3 laws also seem to confirm the existence, if not the nature, of the universe's, the solar system's, clockwork. Science historian Thomas Kuhn comments on the revolutionary split from Ptolemy to Copernicus and Kepler.
In spite of his bad reputation, Ptolemy and his successors developed a really quite magnificent astronomical theory. And what's rarely realized about it is that it predicted planetary position with great accuracy. Now, not quite accurately enough in the event, and people began to worry about it. Along comes Copernicus with a very different theory. In its initial form, it doesn't do any better than Ptolemy's, but ultimately it is improved, particularly by Kepler, so that it does. And the result is now that whereas, let's say, Mars used to be, almost a degree away sometimes from the position it was supposed to be at in the sky, now we can get it much closer. What goes with our ability to do a better problem-solving job is the Earth isn't the center of things at all. The Sun is at the center, or eventually there even isn't any center. And one gets a whole sense of the universe, which must now be infinite, in which the Earth is just one of a lot of planets instead of the central body in the universe.
Galileo Galilei was a contemporary of Kepler's, who was able to make several important discoveries, thanks to the first real technological innovation in the history of astronomy as a science. In 1610, he heard of a Dutchman who had constructed an optical instrument by combining several lenses. Galileo took up the study of optics that he might construct his own instrument. Upon completion of his first effort, he turned it to the heavens, and there such things were revealed to him as had never before been open to man.
It was an enormous window Galileo now opened. He was driven to quickly publish his Messengers from the Stars, quick to make sure he garnered credit for the discoveries. He found 4 moons round Jupiter, a fact which bolstered Copernicus's claim that our own moon orbited round the Earth, while the planets circled the sun. He found that Mars and Venus go through phases like those of the moon, proving they shone by reflected light and not of their own power. He found mountains and craters upon what had always been regarded as the smooth face of the moon. This smashed the long-held belief of planetary perfection and smoothness in the heavens. He saw sunspots. He turned his lenses to the Milky Way, a band of white which had always been believed to be dust, and found that it was composed of individual stars.
Within a year of publishing his discoveries, other astronomers had acquired telescopes, as the new device was called, and Galileo's discoveries were confirmed, and he was accorded much honor, even by the Church and its prominent Jesuit astronomers. Had he chosen not to fight with churchmen over priority of discovery of the sunspots, he might have escaped persecution and been in a position to persuade the world to turn to Copernicus. He already accepted that predecessor's planetary system, and in 1597 had written Kepler,
I adopted the teaching of Copernicus many years ago. I have written many arguments in support of him and in refutation of the opposite view, which, however, so far I have not dared to bring into the public light. Frightened by the fate of Copernicus himself, our teacher, who, though he acquired immortal fame with some, is yet to an infinite multitude of others, for such is the number of fools, an object of ridicule and derision, I would certainly dare to publish my reflections at once. If more people like you existed. As they don't, I shall refrain from doing so.
The Church was happy with the existing clockwork. When Galileo wrote letters in 1614 praising the Copernican system, his enemies among the churchmen were quick to pounce. The Bishop of Fiesole demanded that Copernicus be jailed at once, not realizing the man had been dead for 70 years. Galileo was made to recant his support of Copernicus before the Inquisition. If astronomy were to progress, it would do so outside Italian Catholicism. It would find deliverance in the colder climes, in lands under the influence of the likes of Martin Luther, in Reformed England, an emerging major power which would spread a rebellious theological spirit into the universities and other centers of learning and experimentation, to Cambridge University and Isaac Newton. Newton marks a turning point in the development of astronomy, and not simply for the laws of motion and gravity he articulated. He stood at a point in which man could at last look back and survey what had gone before, examine past discoveries, and make use of this information in finding the right line to push ahead upon. Stephen Toulmin, historian of science.
One has to admit that in its own way, it was not so much geology and zoology, which was the first field of science into which some kind of historical notions were introduced. In its own way, astronomy was an historical science very early on, and people began speculating about the historical development of the planetary system, for instance, before they were really in a position to speculate at all fruitfully about the historical origin of the Earth or about the way in which organic species had developed out of one another. So that this whole business of physical cosmology and the attempt to construct a history of the cosmos, an historical account of the cosmos, has been a legitimate part of natural science, certainly since the time of Newton, even if we don't go any further back than that.
Newton's bust in Trinity College Chapel at Cambridge is subscribed, Newton, who surpassed all men in genius. Strangely enough, this may not be so far from fact.
He was rather careless in reporting his discoveries, and consequently other scientists sometimes achieved acclaim for things Newton had discovered earlier but failed to publish. Such is the case with calculus, which Newton arrived at some little time before Gottfried von Leibniz published his version.
He did achieve proper recognition for the articulation of gravity, the force which actually held those heavenly bodies in motion round the sun, and for Newton's 3 laws of motion.
A body at rest, or in uniform motion in a straight line, remains so unless acted upon by a force. The acceleration of a body is proportional to the applied force, and inversely proportional to the mass of the body. Finally, to every action there is an equal and opposite reaction.
These laws Newton saw working on Earth, and working mathematically in models. By applying them to the universe and the movement of the planets around the sun, Newton confirmed the rationality of Copernicus. It also offered to cosmology and cosmogony laws with which to judge future models of a universe grown beyond the solar system, future projections of the history, past and future, of the cosmos. Stephen Toulmin.
The ability to construct an historically accurate narrative about how the cosmos has come to be as it is, this is now as much a legitimate and recognized part of the scientific enterprise, a legitimate and recognized element in the scientific worldview, as any account of the kinds of mechanisms which are there to be discovered in nature as it operates today.
Newton was somewhat over-harsh in evaluating the significance of his own discoveries.
I do not know what I may appear to the world, but to myself I seem to have been only a boy playing on the seashore, and diverting myself in now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me.
All he accomplished was the definition of the force which kept moon tied round Earth, Earth and planets round the sun, and the laws of motion which kept them moving in their prescribed paths. In one sense, he articulated the ultimate guidelines of the clockwork, but his laws would form the basis centuries later for men to extrapolate backwards and forwards from the present universe to universe past and universe future, from creation to consummation.
Man now knew fairly well the workings of the solar system, but though he had moved from flat Earth to sphere to spherical solar system, he still counted that the sum of the universe. The stars in the distance were still the finite wall tied to our solar system as the center of all. But that would soon change, and man would move from a universe circumvented by a solar system a light month wide to a galaxy 400,000 light years in diameter, to a universe in which we merely guess at a width of 26 billion light years.
Earth had already shrunk in significance, no longer even the center of the universe, let alone its major part. It would shrink further, and man with it. But the human mind would expand enormously as it reeled with the difficulty of comprehending a growing universe. And the mind would, perhaps not without a slight trace of arrogance, presumed toward such an outward reaching in space and time as our human ancestors could not comprehend. By 1700, man had a good notion of his solar system, but even astronomers like Kepler thought our system to be the center of the universe, surrounded by a finite vault containing the distant stars. We lacked a true sense of distance and perspective.
Then the astronomer Halley, in 1718, discovered that certain stars, known to science for a long time, had moved. He compared the positions of Sirius, Procyon, and Arcturus with those carefully cited by the Greeks, and found differences so great as to be unaccountable by error on either his predecessors or his own part. The stars were not affixed in a vault, but rather had their own proper motions.
Eventually, astronomers found a method of measuring the distance of the Earth from various stars by parallax. It was found that stars varied in distance from Earth enormously. Procyon was 11 light years away, or the distance light would travel in 11 years. Sirius was much closer, at 9 light years distance. There was depth to the heavens.
The closest star to the Sun is nearly 7,000 times further away than the planet Pluto. The solar system is obviously isolated in a sea of stars at varying distances from us.
As more and more stars were found to have proper motions, it became apparent that those motions did not indicate a general revolution around the solar system. The motions seemed almost random, certainly not such as Newton's law might explain.
In 1666, Isaac Newton studied sunlight passed through a triangular prism. He called the resulting band of colors a spectrum. In this band of color, each color was composed of shades, and each line of shade varied in length. The most nearly red wavelengths were longest, the most nearly yellow shortest.
Further, there were blanks in the colors, dark spectral lines which formed distinctive patterns. By comparing the position of the lines in the spectral light of any star, we can tell whether the light is tending toward red or the other end of the spectrum.
In 1868, Huggins found a shift to the red in the spectrum of Sirius. The star Sirius was moving away from our solar system and our sun. The information was startling, but its implications as yet were not clear. We were still assuming a universe centered on the solar system in a finite collection of stars.
In the meantime, Harlow Shapley was calculating the distances to Earth of little clusters of stars the new telescopes had begun to reveal in the heavens. He assumed that these must be distributed round some center, and by 1913 he had calculated enough of them to estimate the actual universal center was some 50,000 light years from our solar system.
Once again, man's place in the universe was found to be quite unlike the centrality he had imagined. Once again, he assumed his latest discovered expanse to be the extent of the universe. He built a model of what he now calls our galaxy, with an enormous, dense center from which swirled arms of stars. He added satellites to this generalized universe, the two Magellanic clouds, which seemed to be gigantic clusters of stars in close proximity to us and tied to our galaxy. By 1920, that seemed to be it.
Among the objects seen floating in our galaxy were nebula, believed to be either clouds of matter or gas, illuminated by nearby stars, much as men before Galileo believed the Milky Way was a band of dust in the sky. But as early as 1750, the philosopher Immanuel Kant looked through his telescope at the Andromeda Nebula, saw the ball of fuzzy light, and declared it to be an island universe, a separate galaxy.
Kant's notion was naturally dismissed. It removed the wall of firmament from a contained and finite universe. But with the discovery of the Magellanic Clouds, astronomers began to reconsider the proposition. Telescopes continued to improve, spectral study was refined. In 1899, the Andromeda Nebula was found to produce a drab white band of light, rather than the expected pale color a cloud of gas produces. The nebula might indeed be a mass of stars so close together and so far off they couldn't be made out separately. Then again, it might still be a cloud of dust reflecting starlight.
The matter was laid to rest with the discovery of nova, stars which suddenly flare up in the heavens, blaze brightly, and died. By comparing many nova found in the direction of the Andromeda Nebula with one in another part of the sky, found by parallax to be 100 light-years away, scientists finally decided the nebula had to be several hundred thousands of light-years away, and not part of our universe, our galaxy. Kant was vindicated. We lived on a planet in a solar system near the rim of one galaxy, which was but one island universe in a universal expanse immeasurably larger than we had imagined. On the final round in our bid for universal centrality, and apparently lost it. Now that we had an idea of the cosmology of the universe, astronomers and physicists returned once again to the question of beginnings, of the cosmogony as we see it unfolding today. Remember what was said earlier about the red shift of light from some stars, indicating they were moving away from Earth. Scientists worked out similar results from studying the light of distant galaxies, that the galaxies too were in motion, receding from us. Professor Robert Rader of the University of Toronto's Department of Astronomy describes the velocity-distance law astronomers worked out regarding the distant galaxies.
In general, the fainter a galaxy appears to us, the greater is the shift of its spectral lines. And if this is interpreted as a Doppler effect, then the faster it's moving away from us. And since, generally speaking, a galaxy will be fainter if it's further away, you have the idea that the further away an object is, then the faster it's moving away.
Professor Helen Hogg of the University of Toronto explains the development of this idea.
It came rather gradually over a period of 10 or a dozen years as the instruments were pushed further and further out. First, Dr. Slipher had velocities up to hundreds, or I think even up to several thousand kilometers a second, but of the distant galaxies. But the first velocities were of members of the local group of galaxies close to us and not systematically receding from us. And after Slipher, Milton Humason pushed the Mount Wilson telescopes, especially the 100-inch, right to the limit. His exposures there was one plate he took of about 60 hours, as I recall. That is night after night on the telescope on the one object that was too faint for him to see in the eyepiece. The telescope was set by dead reckoning. And Edward Hubble used his results, Humason's results, and together they worked out the velocity-distance relationship.
And one thing that's always impressed me is I think that the first spectrum of an extragalactic nebula that was obtained was that of M31, the nebula in Andromeda, which is actually coming toward us instead of going away.
The universe seems to be expanding. But why? And in what? What kind of space is space? we can assume a flat universe, one in which a ray of light would travel through a perfect vacuum in a straight line forever. Albert Einstein worked out his own laws of gravitation for the solar system and applied them to the universe in general. He accepted the Riemannian model, named for George Riemann, who hypothesized it in 1854. This is a spherical universe in which three-dimensional space curves at a constant degree in every direction. A ray of light would wind up looping back on its own path in such a universe. Infinite space in a paradoxically confined space. Remembering how often man has fled from the notion of an infinite universe, it's not surprising that Einstein's model based on Riemann's finite sphere is so widely admired. Still, we are left with a universe expanding, although it does so within a confined space. With Einstein, we postulate the cosmological principle that the universe would look pretty much the same to an observer standing anywhere within it, be it on Earth or on the planet of Alpha Centauri. How did it get to be this way? Two major models have been offered, the Big Bang and the steady state. Both take the same point of departure, namely the redshift factor, but each describes a vastly different kind of universe. Both promote the notion of clockwork, as they are solutions to Einstein's mathematics of the heavens. But the springs of each are absolutely uninterchangeable. Professor Rader discusses the Big Bang model.
It was Gamow who deduced, I guess in the 1940s, that if one had the type of universe which is represented by a solution that starts from a very dense state and then expands, then because of this very dense state being optically thick, any radiation that was present, and there should be plenty, would be thermalized to that which is the radiation represented by a black body distribution, and that this radiation should then still be around in the universe, and it should have a temperature, he estimated, of the order of 5 degrees K. And it's very interesting, as a matter of fact, that he produced this prediction, I think it was in the late 1940s, and at the same time, an experimental physicist named Bob Dickey, who was at Princeton, was deducing that the microwave background temperature of the universe seemed to be on the order of a few degrees K. And this was a background that he couldn't get rid of in his experimental apparatus, and therefore he deduced that it must be, in fact, filling the whole universe. But he didn't read Gamow's papers. Gamow didn't read his papers. And it wasn't until the mid-60s that the two ideas sort of came together with a big explosion in cosmology.
But what happens if we run Gamow's mechanism backward? What would the observer see in the universe?
If you were to reverse everything at this instant of time, run everything backwards, then we would come to a state when all the existing structures in the universe would be wiped out, and we would ultimately pass the density of nuclear matter, and the amount of radiation in the universe would rise tremendously, and all this would be crammed into a volume of space smaller than the size of a pinhead, something of the sort. This, of course, is a mathematical abstraction, but you get the idea that in the early stage the universe was really dense, and there was lots of radiation around, lots of very strange particles, the particles that high-energy physicists like to talk about and try to create with atom smashers and the like. These were all around in abundance in the early universe. And from that very dense state, about which we don't know too terribly much, the universe expanded as if it were exploding. And it's this expansion that we still see going on today. The reason, of course, is bound up in one of the objections to this type of Big Bang theory, namely that you have to build in certain initial conditions to the theory, and this is what some people find aesthetically unpleasing. They think the universe should determine its own laws, but as with any differential equations in mathematical physics, you have to specify certain boundary conditions to get the system going. And we observe today that the universe is expanding, so we build in the initial condition that this was a Big Bang and that things were expanding. It's perfectly possible to solve the equations and find collapsing solutions where everything goes the other way.
The Big Bang theory offers a philosophical conundrum. It suggests a moment of creation at which point the cosmic pinhead exploded. Why then? Why not some other time? Pope Pius XII admired this theory and praised it publicly for leaving God a little latitude for action. Many scientists who accepted the Big Bang notion disliked precisely this aspect of it, and they produced a variant.
Some other people prefer the idea of the oscillating universe as a subclass of Big Bang universes. This would be one which starts off from the bang, expands for a while, and ultimately starts to contract again, comes back, and then becomes a super dense, hot, very dense object, and then explodes again, bang, and off we go on the next cycle. And some people find this idea much more attractive because, in a sense, it eliminates the question of a beginning because it's just always been going along, bouncing from one Big Bang to the next. And this then tries to get around the idea of an origin without going as far as the steady state model, which also tried to get around the question of an origin, but in a different way.
That steady state model, the child of Hermann Bondi and Fred Hoyle, was based on a very daring hypothesis: the perfect cosmological principle.
The idea of Bondi and Hoyle is simply that they thought that, as a philosophical principle, the idea that they call the perfect cosmological principle, namely that the universe should present the same picture to any observer at any time as it presents to us now, would be a very sound concept on which to build a model of the universe, which they thought could be easily tested. You see, the conventional Big Bang models utilize a principle which is known as the cosmological principle as opposed to the perfect cosmological principle, which simply states that any observer in the universe who takes a picture of it now will see the same picture as we do, but this doesn't say anything about whether we would see the same picture as observers a million years from now, for instance. However, many people feel that because it is necessary to introduce a creation of matter continuously in time in order that the universe may present this unchanging view to an observer, because after all, if the universe is expanding, then galaxies move away from each other, and you have to have something to fill up the space, or the universe won't present the same picture anymore. So in order to fill up the space, you have to make matter. And so you have to have continuous creation of matter in the steady state model. And many people felt that this violated the conservation of energy, mass energy, which is a very basic principle of physics, and they would not like to see this. But in fact, if you ask yourself to what degree the conservation of mass energy has been experimentally verified, you find that the required creation rate in Hoyle's and Bondi's models would not really violate the observed conservation law as far as it's been determined in the laboratory. Now, the supporters of the steady state theory have argued in the past that the same people who were quite prepared to have violations at the instant of creation in the Big Bang models were being somewhat, how should I say this, somewhat silly if they argued against the introduction of continuous creation, which simply did the same thing but spread over a period of time. The figure that I have in mind, which was 1 hydrogen atom per typical skyscraper for several million years. So.
Again, the cosmogony and the cosmology of the universe are based upon models, upon postulates and assumptions believed to be credible, but for which there is as yet no absolute way of obtaining confirmation. Scientists are building models, and they take their cultural taboos, fear of the infinite, as well as cultural values, admiration of clockwork, with them, on even their most fanciful flights of invention.
One creates a cosmological model because he wants to try and describe in some theoretical framework the picture, the sort of the big picture that he observes when he looks out at, or when he looks at observers' plates, what they see through the telescopes. Einstein, I guess, who was the first modern cosmologist, was simply trying to apply his theory of gravitation, which he found fairly successful in the solar system, to see if he could make a model which would describe the universe as it was then thought to be. And it turns out, of course, that we have to oversimplify the picture to make these models to start with. The cosmological models are really an oversimplification. And when you try to make them more realistic or introduce ideas of how galaxies might form and so on, then it becomes tremendously complicated to actually work physics in these things.
Isaac Asimov speaks of two universes, our own existing below the speed of light, and a parallel cosmos existing and moving above that speed. Immanuel Velikovsky has found a large and popular following for his books Worlds in Collision and Ages in Chaos, books that get beyond the clockwork, that hypothesize a universal chaos in which the mechanics of Newton and Einstein are still sorting themselves out, in which planets, stars, even galaxies are apt to collide with each other. Many astronomers believe the galaxy NGC 5128 is at present experiencing such a collision. Present? I should say in the past, for the light reaching us from that galaxy is millions of years old. Time, too, is a parameter of the universe. It forms one of the limits and a major limitation upon man's trying to observe and learn the workings of the heavens. Just how much can we observe?
This depends really on what you would care to define as observable. If you're going to talk about observing galaxies that you can recognize as definite galaxies, then 3C295 is about it, and that's the one that has a redshift of about 0.46, which makes it, what did I say, about 1.5, about roughly 4.5 billion light years away.
Asimov and Velikovsky would take us beyond clockwork. It seems the nature of most scientists to stop far short of such sojourns in the realm of what they would prefer to call science fiction. They await some technological or statistical breakthrough to confirm or reject the present cosmological models.
10 or 15 years ago, it was hoped that radio astronomy would supply the answer to choosing the cosmological model, because the radio telescopes were seeing, or in radio wavelengths that is, objects that were apparently much beyond the range of optical telescopes, and perhaps this would give us a real answer. But in recent years, it seems to have developed that what we learn from radio astronomy in terms of source counts depends very much on the model that we put in. And although Professor Ryle, some years ago, made very much of the fact that his Cambridge radio telescope seemed to be definitively picking up more sources very far away, and that this was evidence against the steady-state model, it now appears that from a statistical point of view, it's questionable whether one can argue that, or whether one can simply say that we happen to be in a part of the universe where there are simply a few very powerful radio sources close by.
We are no longer prepared to describe a nova as a god's eye wink, but we are still dead set in our ways of imagining universal mechanisms. Just as Aristotle could think of no other universal model than a spherical one, because it was his culture's most perfect shape, we are limited in our exploration of the heavens by our own cultural notions of perfection. Again, we are still, in many ways, confirmed Newtonians. Ideas, Beyond Clockwork, written and prepared by W.H. Rocket. Readers Ken Haslam, Cy Strange, Al Maitland, Bill Hawes, George McLean, and Harry Brown. Technicians Lorne Tulk and Frank Burton. Production Bernie Luck. Ideas executive producer is James Anderson. And I'm Jim Robertson. Good night. Good evening. I'm Jim Robertson, and this is Ideas. Tonight, Beyond Clockwork, consideration of the limits of man's universe. La Reine Verte, the Green Queen, Earth. The full extent, the final limit man's mind encountered for several thousand years.
Cosmology and cosmogony. Cosmology is the study of the content and form of the universe. Cosmogony, the theoretical study of the universe's inception, its very coming into being. Man, as the philosopher, then the astrologer, finally the astronomer-physicist. Man has passed through these approaches to the universe and come, in the 20th century, to two ultimate sciences, studies which encompass everything under and even beyond the sun.
Even the philosophers of pre-Hellenic Greece were concerned with the meaning and order and